Good day. Today we are going to talk about, as soon as I find my chalk, we are going to talk about an application problem to integration, finding areas between curves. So this is the data from the problem we're going to do here first. This is information about two race cars. We have race cars driven by Chris and Kelly, and they're in this race, and this gives us data from the first 10 seconds of the race. Every second we have the measure of the velocity of Chris and the velocity of Kelly. So the question is, who is ahead after 10 seconds, which is pretty obvious if you look at those numbers, and more specifically, how far is he ahead? So, how can we use this data to figure that out? Okay, we also have a hint, we're going to be using the midpoint rule. Okay, so since we are dealing with velocity and the question is how far is one driver ahead of the other, again, we can see at every measurement Kelly's velocity is greater than Chris's. Kelly is moving faster than Chris, so clearly Kelly will be ahead according to this data. But the question is, how far is Kelly ahead of Chris after 10 seconds? So we use the fact that we know that, or we restate that question, how much more distance does Kelly travel than Chris in 10 seconds? That will tell us how far ahead he is. Okay, so we know that the function that tells us distance or displacement or position is an antiderivative of the velocity function. So we're going to use that fact. We're going to use the fact that we know this integral from 0 to 10 of the velocity function, v of t dt, would give us the position function, which we normally use S for. Sometimes we use P, you might see P also. The position at 10 seconds minus the position at 0 seconds. So it gives us the net distance traveled, or the displacement. So we're going to use that information. One way we could answer this question is we could just figure out how far did Kelly travel in 10 seconds, how far did Chris travel in 10 seconds, and we could subtract those. Okay, but we want to do something that's a little more efficient than that. And so if we think about this fact, we know we could also compare the difference in their velocities over those 10 seconds, and that would give us the difference in the distance that they've traveled. Okay? So rather than using this separately for Chris and for Kelly, what we're going to actually do is talk about Kelly's velocity, again, because we know that Kelly was going faster, minus Chris's velocity. Okay. And this integral, again, will tell us how far Kelly is ahead of Chris after the first 10 seconds of the race. Okay? And we'll find that that would be easier for us to find, especially in this situation. We are going to approximate this. We don't have actual formulas for the functions, their velocity functions. We just have data points. We just have specific measurements of velocity. So we're going to have to approximate the answer to this question, and we're asked to do that using the midpoint rule. Okay, well, if we're using the midpoint rule, remember that means this is approximately equal to the sum of, in our case, it will be the difference of these velocities and we're finding the difference of the velocities at the midpoint of whatever time interval we're choosing. Okay, so that t sub I bar is our notation for the midpoint of the ith subinterval. And that is going to be times delta t, which is the width of our time intervals, of our subintervals. Okay? So we see in this case, we cannot divide this into 10 subintervals we cannot talk about 1 second intervals in time because we need to know the velocity at the midpoint of the time interval. Okay, so it's very important we're clear. If I used the interval of time from 0 to 1, I would have to know the velocity at 0.5 seconds. I don't know the velocity at 0.5 seconds. Again, when we take the midpoint, we're taking the midpoint of the time interval. Okay? We're not taking the average values of two consecutive velocities. I'm not taking the midpoint from 0 to 20 or from 0 to 22 or anything like that. I'm only taking the midpoint of the time interval. So I have to use data I have. So we see that the most specific we could get, in this case, if we need to have a midpoint value for the velocity in each time interval, is that we could use 5 subintervals, or 5 time intervals. So I'm going to use from 0 to 2, and then the midpoint of that is 1, and so I have my velocity values at 1. And then I'll use from 2 to 4, the midpoint's 3, etc. So we see that our n is going to be 5. We're going to divide this into 5 subintervals, and what we're going to do then is take the, I'm not going to write this all out, but we would take the velocity of Kevin minus the velocity of Chris at each midpoint of each 2-second subinterval. And so we'd have all the odd numbers of seconds. 1 second, 3 seconds, 5 seconds, 7 seconds, 9 seconds. Okay? So that's what we're actually going to do. And then, so I'm not going to write that out as I said. And then we're going to take that times delta t, which is the width of or the length of time of each interval, which is 2 seconds. Okay? So let's go ahead and do those calculations then. Okay. So, again, what we're adding up, we're doing a summation. So I'm just going to add up the difference in velocities at each odd numbered second. So at 1 second, Kelly is traveling 2 feet per second faster than Chris. Okay, so that's 2. And at 3 seconds, the difference is 6, 52 minus 46. At 5 seconds, 71 minus 62 gives us 9. At 7 seconds, 11. And at 9 seconds, 12. Okay? So again, where did I get all these numbers? I got them by subtracting the difference in the two velocities that I'm considering at each one of our midpoints. And then I take that entire thing times 2. So 2 plus 6 plus 9 plus 11 plus 12, that's 20, 14, and another 20, so that's 40 times 2. So we see, I think I said meters per second for this, for these measurements. So we see that after 10 seconds, our estimate is that Kelly is ahead by 80 meters. So there's the answer to the question.